Weil. Wow.
Hello everyone, my name is Weil. My throat's beginning to act up, so I'll apologize in advance if I start to lose my voice. I'm a little bit embarrassed to say that I've been working on Ceph for almost 10 years now. Usually when I give talks at conferences, I tend to give sort of a high-level overview of what Ceph does, how the architecture works, the various ways that you can use it. Today I'm going to try something a little bit different, and I'm going to talk specifically about the object storage layer in Ceph called RADOS, and how you can write applications that talk directly to that storage layer. So I'm going to begin by setting the stage a little bit and try to motivate things by giving a sob story about someone trying to scale out a really simple web application and dealing with the storage part of that. I'll very briefly talk about what Ceph is, what some basic features of the architecture are. And then I'll shift to looking at Librados specifically, the interface it used to talk directly to the internal object storage layer, all the various crazy things it can do. And I'll try to finish up with an email use case that sort of demonstrates how you might build an application that's designed specifically to use that storage backend. Feel free to interrupt me anyway, anytime and ask questions. So imagine you're still in college, you're living in a dorm room, and you decide to write some simple web application. You know, maybe you're scouring images off the web and overlaying cute quotes on top of them, something like that. But you have a single server, you're writing a bunch of files to a directory, maybe they're JPEG, something like that. Life is simple, primarily because you don't have any users. You send an email to the campus email list, suddenly you have some users, so you move everything over to some dedicated servers, maybe you get something from the planet, something like that. And you realize that you have to centralize your storage, so you have a number of web front ends and everything's NFS mounting some file server. You know, maybe it's just a Linux box, maybe it's a NetApp, whatever. But life is pretty simple. You don't have to change your application at all. Your site begins to grow, people actually start to use it, and you realize you have to scale up. So usually this means you buy a bigger, more expensive file server from some name brand vendor, max out your credit cards. That works for a while. But at some point you realize that the cost of these appliances tends to be nonlinear in the amount of work you can actually get them to do. And solution, eventually you realize that you need to scale out. So the usual approach is to hash the name of the file content or the file name or something like that, and use that to distribute across some number of servers. So you hash the content, hash modulo the number of servers, mount a whole bunch of them behind things. Everything's fine. Your site continues to grow. Until you start to deal with sort of the various problems I'd handle just by having to manage all these machines. So your file servers start to fill up, your directories get really big. That might be a problem just for administrators who do ls-l. It might be that the file systems that they're running don't handle large directories, although that tends not to be a case these days. So the usual approach here is that instead of hashing across file servers, you hash across a bunch of shards, we'll call them, smaller directories, and you have lots of these shards stored on each server, which means that when you add new backend storage servers, you can sort of migrate these chunks of your data set independently to other machines. Probably you're using some combination of rsync and SCP. Maybe you're doing some trickery to try to maintain a consistent view of things even though your web application is live and it's reading and writing data. Maybe you just take it down for a few minutes and hope that nobody notices. That's usually actually what happens. But in the end, you realize that it's actually 2014 and not 2004. You're essentially reinventing the wheel yet again. You're doing sort of this, re-implementing this ad hoc sharding approach where you have to break your data set into pieces and distribute those across servers, balance that load across lots of servers. And we haven't even started to look at the issues of reliability, whether those servers actually fail and whether you need to replicate across them and so forth. But really we want to avoid having to reinvent the wheel. And so in particular, if you're the person who's writing this web application, you don't want to have to think about any of these details. What you really want is some sort of magical distributed storage system that's going to sit behind your web application, and it's going to deal with all these nitty-gritty, dirty details of scaling things, sharding your data across multiple servers, rebalancing when you add new servers, replicating, migrating, healing when there are failures, all that good stuff. And in exchange for that, usually you're willing to give up some flexibility. So even though you're writing to a file system, you don't need to rename files, you don't need hierarchical directories, you're actually probably fine with the flat or flattish namespace. And life would be much simpler if you took this approach. Now, turns out it is 2014, and there are a number of different solutions that'll sort of fit this bill. Today I'm going to talk about Ceph, because that's the one I know all about. But there are others, I'll review some of those towards the end. So at a very high level, Ceph is a distributed storage system. We say it's distributed because it's designed to scale out to a very large scale, so tens of servers to tens of thousands of servers, terabytes to exabytes, so very large. It's designed from the ground up to be fault tolerant, so there's no single point of failure, and you can deploy it on commodity components that may or may not be very reliable. And it's designed to be self-managing and self-healing so that when disks fail and hosts go down and so forth, the administrator doesn't have to directly intervene. The system will sort of deal with that on its own without too much fuss. Some very basic architectural features. Ceph is designed around a number of smart storage daemons. The basic motivation here being that centralized coordination of a large number of very dumb devices is a lot of work and doesn't tend to scale very well. So Ceph takes sort of an alternative approach where we have a number of what we like to think are very smart devices, or smart daemons running on top of stupid devices. And they use peer-to-peer type protocols to coordinate and have some sort of emergent behavior that gives you the sort of strong consistency and replication and so forth that you want.
I'm sorry, did you just say you're building Skynet?
Yeah. If only. Not yet. So the other key feature is that Ceph is built around a flexible placement algorithm called Crush. The basic idea here is that the system has some awareness of the hardware infrastructure across which it's deployed. So you have disks and hosts, hosts and racks, racks and rows. And then you have a hash algorithm that's smart enough to distribute your data across that infrastructure based on some basic policies. So you might say that I want 3 replicas of every object, but I want them separated across racks or maybe across data centers, whatever your policy might be. And the system is smart enough to do that using a hash placement algorithm that will avoid a metadata server. Yes?
So with that hashing, if you have a really hot shard, can you intervene and tell it, look, I want to distribute that one?
Yeah, so the question is, what happens if you have a very hot shard? Can you intervene? The easy answer is that normally you don't have to, because you're hashing objects randomly across shards and then the shards across servers, and so your workload tends to be very distributed. If you had like one object that's extremely hot or you're very unlucky, then you would have a problem. And there are certain instances where you can tell the system to push load off a particular server if that happens. So there are ways to sort of work around that if you need to. But in the general case, it's not necessary because things are sort of randomly sprayed across all your servers. But the last thing, and perhaps the most significant sort of design thing, at least from the object storage layer's perspective, is that there's no metadata server or proxy that is necessary for finding objects. So the client library is smart enough to know what the topology of the cluster is and what this hashing algorithm is, and it can calculate and go directly to the server that has the data that it needs. And so you get clients that have sort of massive parallel access to all storage servers, and they tend to have direct access without a lookup stage or some sort of proxy. So at a very high level, Ceph is built around what we call RADOS. This is a distributed object storage layer that's responsible for actually storing all the data in the system. This is the part that scales from tens of servers to tens of thousands of servers. It makes sure that all the data objects stored in the system are replicated across multiple nodes, that they're distributed properly, that when you add a rack of storage, things sort of balance out. When nodes fail, the things get replicated. All of those sort of details are handled by this distributed object storage layer. So from the perspective of somebody that's using it, aptly named Librados, they can just say, write this object into the object store, and everything is sort of handled by the RADOS distributed object storage layer. So Librados is the client-side library that's used to access this distributed object store. You can bind it to applications in C and C++. It's just a shared library, and there are wrappers for various languages, whether it's Python or Erlang or PHP or whatever. But on top of this sort of basic object storage service, distributed, highly reliable, highly available service, and we've built a number of applications. So one of those is the RADOS Gateway, which gives you a higher level RESTful object storage interface that's compatible with Amazon S3 and OpenStack Swift. So think HTTP, gets and puts, that sort of thing. There's also the RADOS block device, which is a virtual disk that's backed by objects across the storage server, across the storage cluster, and that's supported by modern Linux kernels and by KVM and Xen. So you can have virtual machines with their virtual disks backed by the storage cluster, and that supports things like snapshots and so forth. And finally, there's CephFS, which is a full-blown POSIX distributed file system that distributes all its data across the storage servers. And the basic idea here is that because we built this reliable and highly available object store, building these higher level services is much easier because we don't have to worry about replication and data distribution and so forth. That's all pushed down into the lower levels. And it turns out that in the beginning, RADOS was actually pretty simple. There weren't that many things you could do with objects. You could just read and write them, and it would distribute them and replicate them. But as we built these higher level services, we realized that there are certain capabilities that were really useful for building sort of coherent, snapshotable, highly consistent services that could be pushed down to the lower levels that would make all of that work much better. And the end result is something that we think is pretty interesting, and I'd like to think that would be useful for other applications that need sort of scale out storage. So what is Librados then? Librados is a native library for accessing this distributed object store, RADOS. It's just a shared library with bindings in all these different languages. It gives you, again, a direct data path to all the storage nodes. So it speaks the native Ceph protocol on the back end, and the client node talks directly to the storage server that has the data that it needs. And it hides all the details of data distribution, migration, replication, and node failure. Your application doesn't have to worry about any of that. That's all handled behind the scenes. So at the core of all this is the basic data model that we support. So you're storing objects. Object is sort of a lumpy unit of data that has some name that you can choose. It can be foo, some string of digits. There's some data associated with that object. That's an opaque byte array, so it looks sort of like a file. It can be anywhere from bytes to gigabytes, and you have byte granularity access to that. So you can truncate it, you can override a random extent to it, you can append to it. All the sorts of things that you can do with files, you can do with objects. Objects also have attributes associated with them. So these are small key value pairs, things like version equals 12. The way that they're stored, they're intended to be very small. It's optimized for that case. So you can make them big, but it won't work very well. But the last and probably more unusual thing is that you can also store key value data inside an object. So that gives you sort of random access, insertion, removal, and listing, kind of like you'd get with a NoSQL type of product or like a BerkeleyDB file. And the keys can be some number of bytes long, and the values can be anywhere from bytes to kilobytes and maybe even megabytes. A little bit more about that later. Objects exist in the cluster inside of an abstraction called a pool, which is just a logical collection of lots of objects within a sort of a separate independent namespace. You can name your pools whatever you want. But the main thing is that pools have some basic properties associated with them. That's the replication and data placement policy. So you might say that this particular pool has 3 replicas and it's distributed across different racks in my cluster. This other pool only has 2 replicas distributed across these hosts. And maybe this other pool is stored using erasure coding separated across hosts using this particular scheme or whatever. The erasure coding isn't there yet. It's coming in the Firefly release, which is coming out in February. So sort of getting down to the nitty gritty here, this is a simple hello world type program. So I'm going to use the C++ interface because that tends to be my language of choice, at least in user space. So you'll include the header file, of course. You just install the package and so forth. You would create a cluster handle that says this is the RADOS cluster I'm going to talk to, indicate what user you're going to authenticate as, and call the connect method. Behind the scenes, this is either going to look at the configuration file that's installed in etc Ceph, or you can add some additional calls to specify which server you're going to connect to and so forth. And that'll go out, it'll authenticate, discover the topology of the cluster, and come back. And then you create what we call an I/O context, which is essentially sort of like a file handle that's associated with a particular pool. This is a thing that you use to do actual I/O operations against the cluster. In this case, we're going to talk to a pool called myPool. And next, we'll create a buffer, put hello world in it, and call the write function to write to an object called myObject, and we'll put that data in that object. Now it'll go out to the cluster, tell it to write. It'll get applied to all the replicas. We'll get an acknowledgement back when that's safe and sound. We can then go set an attribute on the object that sets what particular version it is. Yes?
Can I just ask about that acknowledgement of the write?
Yes.
Can you set the policy for a quorum, or that you only have one, or you have all?
So the question is whether, when you're doing the write, if you can get an acknowledgement when you have a quorum as opposed to all the replicas. And the short answer is no. Ceph is very pedantic about making sure that all replicas are consistent. And so you get all the acknowledgement back only when you get all the replicas. And that's because we don't want to deal with cases where you only wrote to 2 out of 3, but then those 2 failed and now you have an old version. We want to be very careful that we actually know that the thing that you thought was written was actually written, and your code doesn't have to worry about the case where it actually wasn't. There are other systems that are designed, when you can deal with those sorts of ambiguities, then you probably want a different type of system than Ceph. So the next operation will just set an attribute on that object. Again, that'll go out and do it, reply. And of course, you can read that data back. You can tell it to read from my object again into a different buffer, some number of bytes at offset 0, and we assert that we actually got the right data back. So nothing too crazy here. This interface probably looks pretty similar to any other sort of storage interface that you would use in any other environment. So the first thing that sort of distinguishes Librados from other systems that makes it interesting, I think, is the idea of having object transactions. And this is basically the ability to group a number of operations on a single object into a single request that's shipped off to the cluster and applied atomically to that object. and ensures that that entire transaction is applied exactly once. So as a simple example of this, we can rewrite our hello world example as an atomic creation transaction. So we prepare all our buffers, and we're going to write hello world and set this attribute. We declare this object write operation structure, which is essentially a description of the transaction that we're going to apply. And we simply call methods to sort of build up that transaction in memory, all the different operations that we're going to do. So first there's going to be an exclusive creation that'll succeed if there's no object and create it. If the object already exists, it'll error out with an eExist. Then we'll write all the data and then set the attribute. And finally, we call the operate method, which actually says, okay, take this transaction, submit it to the cluster, and actually apply it. And that'll either succeed in its entirety or it will fail. So that's all well and good, but it turns out there's more you can do here. You can also have transactions that are conditional. So you'll notice that that create event would abort if the object already exists. So you can actually have steps in your transaction that if they fail, they'll make the whole thing abort. So typically, the strategy here is to create guard operations early on that assert that some condition is true. For example, they might verify that an extended attribute has a particular value, that the object version is some particular version, something like that. And that means that you can do the equivalent of atomic compare and swap operations from the client's perspective that are enforced by the storage system. So you can have lots of clients in your system coordinating implicitly via the storage system without having to have some sort of locking or coordination layer that you build yourself on top of things. So again, moving on from our hello world example, say instead of saying world, we actually wanted to say Perth. And so we can prepare a transaction that has the new data that we're going to store in the object, the expected old value of the attribute and the new attribute, and prepare a transaction that the very first step, it asserts that the version attribute that's already on the object has a specific value. That's what we expect, the one that we set before. And assuming that's true, then the transaction will continue. We'll replace the data with some new content and set the version to version 2. And when you submit this to the cluster, it'll do that validation. If it's true, it'll apply the transaction to all replicas and then return to you. So the nice thing here is that you could have a similar transaction that's being sent from every other city in the country trying to choose a different city. And only one of these is actually going to succeed because only one of them is going to be the first one there and it's going to change from version 1 to version 2. So the second interesting thing that you can do with Librados that's a bit unusual is that these objects can store not just byte data, like a file, but they can also store key and value data. So each object can store this key value data that's completely independent of the file data. So you can actually have an object that has all these different types of data stored, sort of encapsulated within that logical unit. And the main thing with the key value stuff is that it gives you random access, insertion, deletion, and range query. So key value, you have a table of names and inodes or whatever you want to store there. So this is really good for structured data. And we use this internally with a number of other Ceph services. So for example, the RADOS gateway, which is providing this S3-like, Swift-like, higher level RESTful interface, has to maintain an index on the user buckets that indicate what objects exist in that bucket so that you can go back and you can list them later. And so we store all that index data in a key value object. And so when you're actually creating a new object, you just send an operation that says insert this new value into the index, and the client side doesn't have to know how big the index was or what offset to write to, any of that stuff. The storage system sort of manages all that low-level detail for you. Similarly, the Ceph distributed file system uses these key value objects to store directories. So essentially, it's just a map of file names to inodes. And so when you do file creations or inode updates or whatever, it doesn't have to do an expensive sort of read, modify, write operation to maintain some special format for the directory data. All that's handled by the low-level storage library on the storage servers. And the client doesn't have to worry about it. The third unusual or interesting thing that Librados does is gives you sort of a very powerful, although somewhat difficult to use, infrastructure to support snapshots. So the snapshots in Ceph can be either at sort of a high coarse pool granularity, or they can actually be as narrow as an individual object granularity. And the motivation here is that we want to support snapshots on smaller pieces of data in the system. So for example, for the RADOS block device, you have a number of disk images. RBD allows you to create snapshots on a per image basis, and that applies only to the objects that are storing data for that particular data storage, that disk image. Similarly, for the Ceph file system, it has the ability to create snapshots for any directory or subdirectory in the system. And we use this capability to apply only to the objects that are storing file data for files contained within those directories. So the cost is that there's some coordination with the client code that's required to make sure that you're sort of keeping track of which snapshots apply to which objects. and that has to get fed back into the cluster when you're doing writes. But the flip side of that is that it allows for point-in-time consistency from the perspective of the client. So in contrast to snapshot solutions that are based on NFS servers, where it's the server that's actually doing the snapshot, and things like asynchronous client write back from their caches isn't sort of coherent from the snapshot's perspective. In Ceph's case, we can actually apply that serialization point on the client side and have a sort of stronger consistency semantic. And of course, it goes without saying that all this is copy on write, so that snapshots don't actually consume any space on disk until you actually modify data that was snapshotted. And at that point, you have to maintain 2 copies. The fourth thing, and one of the most exciting, I think, is the ability to implement new classes in RADOS. So if you think of things in sort of the high-level object-oriented sense, where you have some piece of data and you have another number of methods that manipulate that data, you can think of RADOS as implementing some very basic methods like read and write extent, set attribute, delete, things like that. RADOS classes allow you to implement new code, new object methods that are based on the existing functionality, compile that code and actually embed it into the storage system and execute it there. So there's sort of a simple plugin API that lets you write these new methods. The admin will build it into a shared object and deploy it on all your object servers. And then the clients can invoke that code using the RADOS API. So this sort of comes in 2 flavors. You can have read-side methods that will send a request, method invocation off to the storage cluster. They'll do some processing and return the result. And then there's the write-side methods where you send a request. It'll maybe do a read, modify, write, do some computation validation, generate a transaction that's consistently and safely applied to all the replicas on that object. So a simple example of a class method you might implement, this one computes an MD5 sum on the object contents. So there's, this is a simple C method that you implement. There's this context argument that you can mostly ignore. It's used for internal tracking. The important thing here is that there's a buffer that's being passed into your function, and there's a buffer that's being passed out of it. So this is the data that, effectively, the arguments that are being passed from the client. This is the return value, the return data that's being returned for the read-side methods. So in this case, we stat the object, figure out how big it is. If the object doesn't exist or we get an error, we just return immediately. We read all of the data for the object into some in-memory buffer. And then we call the MD5 library to calculate the digest, which is 128 bits of gibberish. Append that to the output buffer that's going to be passed back to the client, and then return success. And in order to invoke this from some client code on the other side of the network, we'll make this example a little bit more interesting by doing a compound operation where we're actually going to be performing multiple read operations in the same sort of single request. So we declare an object read operation, just sort of a compound transaction. First, we're going to stat the object, figure out how big it is, what its modification time is, and then we're going to invoke the class method computeMD5 that we just looked at, which is part of myclass.so, whatever, which is deployed to your servers. And we're going to pass in no data because it has no arguments. Oops. And the return result is going to be passed back in the out buffer. Yes?
So all of these custom classes only need to be deployed on the OSDs, on these servers?
Right.
So there's nothing that has to happen on the client for that to work?
Exactly. Yes. Yes. And it's the administrator's job to make sure that actually happens. And then we call the operate method, which gives the transaction to the library. It goes and performs both of these operations and comes back and returns. And at that point, we can assert that we either got an error or we actually got 128 bits of stuff back and printed out. So this is a pretty simple example, but you can imagine there are a lot of different possibilities of things that you can do with this. So sort of going back to our motivating example from storing images in the storage cluster, where each object is a big JPEG or something, you can imagine a class that's actually doing image manipulation. It might be rotating an image and rewriting it. It might be generating thumbnails and returning it. It could be applying some filter to it. You can imagine if you're streaming out structured data in some log type format, you could have a class that is going through and filtering the records and looking for some matching pattern and only returning the results. So instead of shipping the haystack over the wire, you're only shipping the needle that you find. The RADOS block device and RADOS gateway have their own classes that they use, mostly to enforce sort of a clean interface to the objects that are storing metadata about disk images and so forth, so they can do argument validation and make sure you're not storing gibberish in the system. And one of the more interesting examples to come along is a class contributed by a contributor, Noah Watkins, that takes the Lua embedded script interpreter. Lua is a simple scripting language that is sort of designed to be very easy to embed in other applications, and shoves it in a RADOS class. And so you can actually, on the client side, write a bunch of scripting code, send a request up to the storage server, and it'll run it in Lua, and read and write stuff, do whatever you want, and then ship the result back. So it's sort of a probably raises a lot of red flags for people who are worried about security, but also introduces a number of interesting possibilities if you're running in a controlled environment and trying to do interesting things. So all that said, so as I said at the beginning, RADOS began as a relatively simple object store. We were just storing blobs of data to store file data for a file system. And as we developed these other services, the RADOS block device and the RADOS gateway, we realized that it was helpful to push some of this capability down into the storage layer. For the sort of last bit, I'd like to look at sort of an example of a type of application that might be able to take advantage of some of this functionality to have sort of a scale-out storage backend that's hopefully a little bit more efficient and attractive than what the current solutions are. So one of my sort of pet peeves is the way that a lot of service providers deal with email. So it turns out that email hosting tends to be a pain in the butt for a lot of hosting providers. Typical solutions tend to use tools like Postfix and Courier and Dovecot for IMAP and so forth. But it turns out usually people are storing things in maildir format, which is not the most efficient thing in the world. They tend to use NFS file servers, and it tends to hammer them very hard, and performance tends to suck, and it's expensive, and file servers fail, and it's not very nice. Maildir in particular is very inefficient, especially when you're trying to list the contents of a mailbox. It's essentially storing every message in a separate file, and in order to, for example, to get your mailbox list, it has to open up every file and read the headers and get your from and your to and your subject, so you can just list your mailbox. On the other hand, Ceph is sort of an attractive backend from a high level because it already gives you sort of reliability, scalability, so you can just add servers as you need them. Everything's replicated. It has a simple consistency model, so you don't have to worry about these weird issues where things appear and then they disappear, that sort of thing. So the question is, could we make this work? So the nice thing is that the data model for email is relatively simple. Right, so you have messages that contain some sort of raw data, just a bunch of headers and a bunch of body. So that clearly maps onto just the byte array that's associated with an object. So that's pretty straightforward. Sometimes messages have some MIME data structure associated with them. They have some structure. So it might be that you want to index some of that and store it in attributes so that it's easy to access things later. Maybe that's a win, maybe not. I actually don't know enough about MIME to know if that's even a difficult problem. But clearly you can easily map a mail message to an object. That's pretty simple. You also have mailboxes, which are simply collections of lots of email messages. So you have references in the mailbox to all the different email messages that it contains. That'd be very easy to store as keys and values in the mailbox object, referencing the unique message ID for that particular email message. Mailboxes also have things like flags associated with messages, whether you've read or forwarded it, something like that. One of the easy optimizations that you can do here is that usually things like IMAP will do list objects or list messages and get back only the headers but not the message content. So you could easily just take all of the message headers associated with the messages and shove them in the mailbox as the value associated with those key value pairs. So a little bit of extra storage there, but when you list the contents of the message, it's all in one object, it's all in one place on disk. You can list the contents very quickly. And of course, just to round things out, you have users in your mail system and they have mailboxes, and so you'd have some object per user that maps to all the different mailboxes that they have, and of course, mailboxes map to the messages. So relatively straightforward, and it sort of conveniently maps onto both the data portion of objects and the key value capabilities that RADOS provides. So sort of a simple example, the first thing you want to do here is actually deliver mail. So you have a message come in over SMTP, you generate some unique message ID, or maybe just use the one that's in the existing headers. You write the message object, and sort of the last thing you need to do is add a reference to that message from the mailbox object. So you need to add a key value pair referencing the message, but you also need to update the message count for the mailbox so that you know that the size increased. And it turns out that you want to do both of those things atomically so that things don't get out of whack. And so that's a perfect opportunity to use a RADOS class. So you can invoke a method that says add message, and it would write the key, read the old size, increment it, and then write a new size, all in a nice, convenient atomic transaction. So that's all well and good. But what happens when you have an IMAP client that's open and it's idling and it's waiting for incoming messages? When you have that message come in over the wire, you want to make sure that the IMAP client gets notified that something has arrived. So it turns out that Librados also has a whiz-bang feature that we call watch notify. So the basic idea here is that clients can establish an interest in an object, which we call a watch. So they send a request that says, I want to subscribe to announcements essentially that come out over that object. And then clients can also send a notify message that's distributed to all watchers on that particular object. So you can imagine in this email case, you might have a bunch of IMAP clients that have, where the server process has that mailbox open. So they subscribe to watch notifications on those mailboxes. And then when a message is delivered, or maybe when you delete a message from the mailbox, something like that, a notify request is sent. That's distributed to all the current watchers. So that process gets notified that there's been a change. They'll acknowledge back that they actually processed that, and the person who sent the notify finds out that, yes, everybody has heard that I made this change, and things can continue. So that would be kind of nice, because I think currently IMAP servers, they'll sit there and pull on a mail dir looking in the new folder to see if there's been a change, or they'll look at the directory in time or some kludgy thing that doesn't work over NFS. And all of those problems sort of go away when you have sort of a first level support in the object store for the capability that you really need. So I've just told you that Librados can do everything under the sun. There are a lot of things that it actually can't do, so I want to sort of make it clear where it might be a good fit and where it might not be. So Librados doesn't stripe large objects for you. So if you want to store a big 1 terabyte thing, you want to stripe that over lots of Librados objects and not stored in one big Librados object, because the Rados object is all stored on one sort of set of servers as one sort of unit. And this is exactly what the Rados block device and the Rados gateway and the Ceph file system do. They stripe over lots of Rados objects. You can't rename objects. That's sort of antithetical to the way that Rados works, because it uses the object name to figure out which server it's going to be stored on. And so if you rename it, then you have some weird multi-server communication that doesn't work. You can't do multi-object transactions. So we're not a database, and we're not really trying to be. So if you have 2 objects that are stored in the system that need to be updated in tandem, then you need to do the coordination about doing that in a safe way on your own. So usually people use a 2-phase commit or an intent log, sort of tried and true strategies there. And that's exactly what the file system and Rados gateway do. They have their own sort of mechanism for keeping things consistent. Rados doesn't do secondary object indexes. So you can only find an object in the system based on its name. You can't send a query to the system that says, give me all objects that have attribute foo equals bar. It won't do anything like that, although there are other systems that do. So that's a requirement. You can look at those. And you can only list objects by pool in sort of a complete, incoherent way. So you can iterate all the objects in the system, but they're returned in hash order, which is generally not very useful. So if you need to enumerate the things that you've stored, you usually need to maintain your own sort of index that does that. So the Rados gateway has the bucket index for that. The file system has directory objects, depending on your strategy. Yes?
How expensive is that? Is that a conventional operation where a lot of optimized for, or is it like most systems they just don't allow you to even enumerate the keys?
Yeah. So the question is, how efficient is it? It's not something that we optimize for at all. That said, it's not inefficient. It's just inherently expensive, because you're literally enumerating every object in the system. So you'll send a request and you'll get back the first 1,000 entries, and you send another request, you'll get the next 1,000. And it'll do it, it just takes forever. It'll take days to iterate over 1 billion objects, right? So if you need it to be fast, you're probably doing it wrong. That's another question.
Can you do wildcard searches for objects?
The question is, can you do wildcard searches for objects? And the answer is, actually, you can. You can say list objects only with this prefix, but at the same time, it's not efficient. So it'll actually list all objects, and it'll just only returns the one that match. So it's not that big a win. Yeah. So just to put Rados sort of in perspective with respect to other object stores and other sort of scale-out open source solutions. Rados is a strongly consistent object store, so it's a CP system, sort of in the CAP context. It favors consistency over availability. So there are a number of systems that sort of take different design positions within that overall space. So Swift is probably the one that you're most familiar with. It's part of OpenStack. It's a distributed object store that's RESTful. Swift is generally an AP system, so it's typically last writer wins. Uses a RESTful API. The data model is much simpler, so you're storing big objects using a get or put, sort of an atomic thing. You can associate metadata with them, but you don't have sort of all this weird key value stuff that you can store inside of objects. GlusterFS is, I think you'd best describe it as a CP system, although I think it's sort of fuzzy depending on what you're trying to do. And it's specifically a file-based model, so it looks like a file system. Everything is a file. So your application has to be coded to store everything in a byte array. So that may or may not be appropriate for your use cases. Sort of shifting to the other side of more of the database side of things, NoSQL world. React is another AP system that sort of faithfully implements the Dynamo design that came out of Amazon a couple years back. So that means when you have divergent replicas, you have flexible ways to resolve those conflicts in your application. You can do things like 2 different versions of a shopping cart, and they both add something. You're just going to stick them both in there and merge that incoherency in a application-specific way. It has a simple key value data model, generally targeted towards small objects, I think. Although you can store like JSON structured data in the value, and it'll generate secondary indexes. So you can do things like map-reduce queries across it within some constraints. So there's that. And then sort of moving up in terms of complexity, there's Cassandra, which is also an AP system, but it has a much more complicated data model. So it looks a lot more like a database. You have rows and columns. You have this extra time dimension. And it also has secondary indexes. So you can do these sort of SQL-like queries across the data that's stored in Cassandra. So sort of wrapping everything up in conclusion, I think the main point is that usually the first thing that people reach for, at least people of my generation reach for when they're building a scalable storage application, is a file system. But file systems are typically poor matches for scale-out applications. So usually, depending on how you're doing it, you're going to have to deal with all the sort of ad hoc sharding to make sure that you distribute across lots of servers. And it's sort of annoying to reinvent the wheel. The file abstraction is often overly simple for the kind of data that you're really going to store. And at the same time, the other complexity that file systems offer in terms of directories and renames and so forth aren't really important or useful for most scale-out applications where you're just shoveling image data into a storage system. On the flip side, something like Librados gives you transparent scaling replication. Very soon we'll have erasure coding, which is also very exciting. You have a richer object data model, so you can store bytes and objects, attributes on this key value data. It's a rich API with these sort of transaction things, snapshots, watch, notify. And most interestingly, I think you can extend that functionality using this class mechanism that lets you sort of push your own code into the storage layer. So you can push as much of the computation in your distributed system to the actual storage nodes close to the data, and use that as a fundamental building block for your system. So that's it. I have a couple of URLs here. Naturally, the best reference for coding to a new API is to look at the header file that defines the interface. In our case, we have doxygen comments for most of the methods. The C1 is very well documented. The C++ one is slightly less documented. In most cases, we generate the web pages for that. You can go to the Ceph docs and you can find those links. And of course, there's the development email list, and people on IRC are very excited to see people using Librados, so they'd be very eager to help. So thank you very much.
So if anyone has some questions, we've got about 8 minutes to...
Yeah. Florian.
Can you summarize the current state of the Librados interfaces for languages for real world,
like Python? Yes. So if you look at all the languages, the C++ one is the most expansive. It's the one that has support for all these transactions and so forth, because that's the one that we use internally for RADOS Gateway and RBD. The Python bindings are, after the C bindings, the Python bindings are probably the most complete. They're used by there's some RBD wrapper libraries and librd and so forth that are used by OpenStack and some other things. There isn't support for the transactions yet in that interface, although it'll be pretty straightforward to add. It's just we're sort of waiting for a user to ask for it, and they'll do it. The Erlang bindings, I think, are pretty complete. They're sites in production. We have customers that are building Dropbox things, and they're using Erlang. I don't know what state the PHP ones are in. Yeah, I don't know. Oh, yeah? Cool. So you said there's some Haskell ones, too. Yeah. That's very, very exciting.
That's curious. Dropbox is actually Python.
What's that?
Like you were saying about building Dropbox things, I was saying Dropbox itself is built in Python.
Oh, interesting. Yeah. Okay. Yes.
How about the custom processing functions on the OSD? So what's the execution context?
It is, you have to implement it in C. So the question is, what's the execution context for the classes that you implement that are run on the storage nodes? It's written, you have to write your code to a C API, and those functions are invoked directly in the I/O path. So instead of calling into an internal function that's doing a write or something like that, it's calling directly into your code. And your code can call out to RADOS methods to actually do reads and to append things to the currently accumulating transaction, or can do whatever processing it needs.
So basically, I don't want to mess up the process I'm running.
Yeah. Yeah, so you can mess things up. Yeah, so you're running in the same context as the storage server, so you don't want to deploy bad code. If you're worried about sandboxing things more tightly, then you could write a class that implements a sandbox and then runs something in a sandbox. For example, in a Lua script or something like that. Yeah, the question is whether the execution overhead is minimal, and yes, exactly. That's the reason it's done that way.
Just
Yes.
to extend that question, you said you have to implement sandboxing yourself, but are there any restrictions on how much memory that process could use, or if it's run away, it'll just take the whole thing?
Yeah, the question is if there are restrictions on how much memory you can use if you're doing your own sandbox. Currently there are no restrictions. So if you want to use a lot of memory, that's fine. Your OSD process will just get really big, and hopefully your host has enough memory to deal with that. If not, it'll crash or something. So I think if you need an additional level of protection, then you can build in whatever sandbox you want. So originally, when we were designing this, we were considering just building a Python interpreter in and actually using that as a sandbox. But in the end, it seemed useful to be able to also implement native methods that run with higher priority. And you can always implement that sandbox as a class to sort of layer it in, which is exactly what happened with the Lua stuff. Yep. Yes?
It sounds like the operation stuff you were describing supersedes this, but the question I have is, if I've got an IO context and I'm holding a lock on an object, and something else comes along and breaks that lock, is there some way I can find out about that? Like, why will the next operation fail, or what's the behavior?
So the question is, what happens if you have a lock on an object and you're on an IO context and if it gets interrupted? The short answer is there is no locking. So the requests that are generated by the client and sent to the cluster are sort of discrete requests that execute atomically in isolation. So there's no sort of stateful lock that you can take. That said, there is a RADOS class called lock that implements a cooperative locking scheme.
So what does RADOS underscore lock do?
As the RADOS, the class underscore lock? Is that what you're, sorry?
We're using the CA API.
Yes, so there is, in the CA API, there's a RADOS lock, and that is actually, those are just wrappers around calling the lock class. So it's purely cooperative locking. So it's similar to POSIX locks, where the system will keep track of who holds locks, and you can break them by just removing their entry. But it's totally cooperative, so they only enforce anything if you actually check to see if you hold a lock or not. So just to sort of clarify, the way that's usually used is with the block device, for example. You can take a lock on a device, and then you use it. And if somebody else comes along and they want to lock it, they'll try to take the lock, they'll fail. They'll break your lock and blacklist your identifier, your cluster ID, and so you will no longer be able to talk to the cluster, so they'll fence you out, and then they'll break your lock and then take over.
The transaction stuff, what release did that have in performance? It's still in progress?
What releases?
Transaction stuff, is that now out there?
Yes, yeah, so the question is whether transaction stuff is there, and that's yes. Yeah, so that's used extensively by the RADOS gateway and the RADOS block device. Yeah.
Does that mean that there's no locking then for any of the requests you do? If you're reading and something else is simultaneously trying to write to it, you're not going to block the
Right.
issues?
Yeah, so the question is whether there's blocking if you have simultaneous read and write requests. The short answer is that it's essentially serialized at the server side. So the request will come in, they'll get in a queue, the read will happen, and then the write will happen, or vice versa. So there's sort of an implicit ordering.
Just succeed or fail, but you won't block waiting for
Right.
something.
Right. It could be that you send a request and it takes a long time because the cluster is busy doing another operation in front of it that's slow, or maybe there's some recovery going on and it has to fetch the right copy of that object or something like that. But in general, there's no statefulness in the request that you're doing. So unlike a traditional file handle or something, it's sort of an atomic unit of operation. Yes.
Have you guys done any real-world comparisons of NFS performance versus CephFS if it's accessed over the network?
Yeah, the question is whether we've done real-world comparisons of NFS and
I'm
CephFS.
interested in what the overhead is, if there is any.
So can I ask the same question against a real file system like Lustre or something?
The short answer is we haven't done any performance comparisons on CephFS recently. So most of the performance testing I did was back when I was working actively on CephFS specifically. And that was mostly around making sure that the metadata paths were optimized so that you wouldn't actually wait for disk I/O when you're doing things like file creations. So I don't have any sort of good numbers. I think generally it's just going to depend on how fast your RADOS nodes are. So on the client side, generally you can saturate the network interface. It's shipping the pages directly to the Ethernet or whatever the network stack without copying them and so forth. So it's really just the speed of your network interface that's limiting you on the client side. On the server side, it's just how fast your disks are, the fact that it has to replicate it on multiple servers, so there's some more processing overhead. It's writing it into a file system, and so there's some overhead there. So it'll slow down, but
So the fact that
there's
there's
no.
a translation layer between a POSIX interface and the object backend is negligible?
Right. So the question is whether the translation from the POSIX file interface to the object interface is significant. And I think no, particularly on the server side. So all that's really happening is when you do a POSIX write, it's going directly into the page cache. When it does write back, those pages are being passed to the Ceph driver. It's calculating the striping and just mapping those pages to a particular object, and it's just shipping them over the network to some storage server. And then the storage server is handling the details of replicating it across multiple nodes.
Last question.
Yes?
How does it handle latency? Like your consistency model, would that stop it being used from, say, between countries?
Yeah, so the question is, what do we do for multiple regions, high latency links, running a single cluster across multiple countries? So we generally don't do anything special for that. So a main feature or whatever property of RADOS is that all writes are synchronous. So it'll write to all replicas of the object. Once all the acknowledgements are gathered, then you reply back to the client. So you can spread a cluster across a wide geography and very slow links. And it just means that those writes are going to be really slow. And if you can tolerate that and you don't care, that's fine. And if you can't, then that's not a good idea. That said, there are lots of users that distribute Ceph clusters across multiple data centers in I guess small countries. For example, typical European countries have only a few milliseconds to get from one border to the other, and so they can actually just distribute the cluster around the country. And those latency levels are acceptable for those particular use cases.
Sorry, to add to that question is, what about network splits?
The question is, what about network splits? So Ceph is designed to deal with that gracefully. So there are a collection of nodes, a subset of the cluster that are called monitors that run Paxos essentially. And so there's majority of voting essentially. And so whichever part of the cluster you happen to be in that can access the majority of those monitors is the one that has the consistent view and can continue reading and writing. And then the other people who are on the smaller partition can't do anything. Yeah, so that's exactly where the AP versus CP thing comes in. Other types of systems in a partition event let you write to both replicas, and then they resolve that conflict later. In Ceph's case, the types of applications that we want to support, like block devices and file systems, we need sort of strict consistency and coherency, and so we don't allow it.
Great. All right,
All
thank
right.
you very much.
Thank you.